Hey everybody, this is Jim Janossy. I'm just introducing here the lecture for January the 27th. This is lecture number 8 in CSC-200. In this lecture, which I gave in the classroom this morning, and which was recorded by Course Online, what I cover is a bunch of pages in the middle of Unit 2. First of all, the material covers information about the beginnings of office automation software on mini-computers and why that development occurred there instead of on mainframes. And from that point on, we can take a look at the very same types of software on microcomputers, which came on the scene in the 1970s. Then I skip to a finish-up of large-scale computing that actually comes at a different point in Unit 2 when you'll see the printed materials. It deals with weather modeling and nuclear explosion modeling, things that require very large-scale supercomputers in order to be done on a timely basis. Then finally, towards the end of this lecture, I cover something at the totally other extreme of computers, embedded computer systems, which are small machines dedicated to specific processes in controlling other machinery. For example, in the fly-by-wire systems that exist in aircraft or in multiple places in your car, controlling things where the computer actually reads sensors and gives outputs to other devices to control the machinery. That deals with what's called a servo mechanism, where a mechanism essentially keeps an equilibrium between inputs and seeks to control machinery that in some way is providing those inputs. That'll become a little more apparent and clear to you as soon as we take a look at that. So without further ado, here is the lecture number 8 for CSC-200, which occurred most recently on January 27th, 2011. What I'm going to be doing today is going through about 6 pages that deal with Unit 2. And if you took a look at the original table of contents, you'll notice that I had skipped over some things in talking about supercomputers the other day. I'm sort of filling in the gaps here, and you'll see me talking about some earlier developments and then office automation software. So what I'm going to do right now that the course has been properly labeled, let me get out of PowerPoint. Now, you can see on the screen that the more interesting part of this discussion is going to be what I present in slides and not my smiling face. What we're looking at here, let me sum up for you very quickly. Early on with the computer market, IBM was not in the forefront of the movement. When digital computers were developed, they were developed by researchers at universities, and they were one-of-a-kind machines, and it was very experimental. And government grants were involved in doing this to fund work for the World War II effort in the U.S. The couple of researchers, Eckert and Mauchly, decided that there was some commercial prospect to these types of computers, and they were the ones who formed a company named UNIVAC that in 1950 sold the first commercial computer to the U.S. Census Bureau, which was kind of ironic because 60 years earlier, the precursor to IBM's formation, the tabulating machine company and the inventor Hollerith, had sold the first key punch machines to the U.S. Census Bureau. Every 10 years the census comes around. It's a lot of work tabulating up millions and millions of people and the facts about them. So by 1890, the need was present to store data mechanically and be able to read it back mechanically very rapidly. Well, IBM bought up those interests, and from around 1912 onward, IBM became a big force in the business world by providing equipment that did things with the kind of card that you see here on the screen. This is a punch card. You probably haven't seen one. They haven't really been around for about 30 years. They were pieces of paper about the size of a dollar bill, and it had 80 columns. The printing on there just indicated where the columns were. The printing really didn't matter. You ran this thing through a card punch, and when you pressed a key, it would punch holes in a column, indicating what that character was. Up at the top, we see here, and let me just make that a little bit bigger. Up at the top, we see the printed out value of what's in the column. But this printed out value is for us. It's not for the computer. The computer would understand the pattern of holes here, and there was a different pattern of holes for every different character and number. Well, what does this do for us? What it did for business
It allowed business to tabulate all sorts of records. And IBM developed a very big business in the 40 years from 1912 to 1952 or so, making equipment that punched these cards, making the card stock itself, making equipment that would read these cards back and sort them mechanically and physically into various piles, into various sequences, sorting the data. This was of interest to business because business has to mash through a lot of numbers for accounting purposes. And IBM was very wealthy. In fact, one of the little-known facts about IBM was that Thomas Watson, the man in charge of it in the 30s, had kind of a fondness for Adolf Hitler. And IBM did a lot of business with Germany, and leading up to the Second World War. Unfortunately, it's really kind of a shame to the corporation, but its equipment was used to facilitate the rounding up of the Jews for the Holocaust, because the census that had been done in 1933 in Germany was stored on these kinds of cards, and the characteristics of the people, including their religious preference, was stored on those cards. So these could be gone through very quickly to round up people who had answered that they were Jewish or some other persuasion that was not of very much appeal to the Nazis. Well, be that as it may, the IBM prospered with this kind of business. When computers were developed, electronic computers, IBM saw them as competition for this kind of business. The people who developed those computers had no real fondness for punch cards. They adopted a different type of communication device to deal with computers, the computers that they were developing, and that was the teletype machine. And I'll show you a picture on the next page. The teletype is like a terminal. Although it's a mechanical device, like a typewriter, you press the keys, and it sends a signal out, a unique signal for each key depression, and it prints that character on a piece of paper. That signal can be interpreted by the computer, and you can use it to communicate with the computer. So the earliest computers actually did business that way. And IBM saw that as a big element of competition. So when it first came out with its electronic computers in the early 1950s, it arranged those computers to communicate using punch cards, because that was its established business. And as a result, because IBM's marketing power was very great and their manufacturing and engineering capability was very great, they began to dominate the computer market into the 1960s. And a lot of what was developed in computers at that time was aimed at punch card storage of information. That's why two languages that were very prominent early in computing, Fortran and COBOL, were both designed with 80-character card images in mind. Later on, when IBM adopted electronic terminals, many of them were set up simply to do business with punch card images, that is, electronic images, 80-character rows of information called records. And that's perpetuated to the present day. IBM systems are controlled by a job control language that resides on card images of 80-character length. So the impact of IBM's earlier business is still felt today, at least in IBM mainframes. Well, let's take a look at something that was beginning to compete with IBM mainframes in the 1970s. In the 1970s, some engineers, electrical engineers, electronic engineers, started to use the circuitry that had become available, gradually miniaturizing into integrated circuits, to build mini-computers. Mini-computers were still expensive. You wouldn't exactly want to buy one. They cost hundreds of thousands of dollars. And they were little mainframes. But the big difference is, down here you see the device that's being used to communicate with this is a typewriter-looking device. This is a teletype machine. And this machine you talk to with that console, and users would use the same type of console. They wouldn't be oriented to putting data on punch cards or putting control statements on punch cards. They would type them in this way. This eventually, and rather quickly, developed into the idea that the computer could do more than just crunch numbers. That's what a lot of engineers and scientists used it for. But in order to put statements together for programs, you had to have a text editor, that is, something that would type up statements. And instead of using statements on punch cards, you would want to type those statements up here and perhaps put them in a file as ASCII characters. In order to do that, you need a text editor, at least a text editor. Text editor, you might think of as a word processor, but it's very dumb. It has no formatting capability. It simply captures characters. And an equivalent on IBM PCs is the Notepad program. You can find that in accessories. It's a very crude program. It doesn't allow you any real formatting, although it might allow you to change the format of letters on the screen, but it simply captures ASCII characters. And when it prints things out, it won't print them out with any particular kind of formatting. It's not what you would use to generate correspondence. However, in the early 1970s, people using mini-computers, and as programmers using them, started to write programs that turned into word processors. And this is where productivity software and office automation came from. Something else that these mini-computers were able to do, because everyone talking to the mini-computer was tied into it with a communicating device, a terminal, it was fairly easy to develop a messaging system. And that was the precursor to email systems. So mini-computers early on, because they were oriented to this interactive communication, they set the stage for people realizing that you could use the computer as a messaging system, and that was a very big deal in business. You could send messages to other people who were at least on the same computer. Now, the internet didn't exist at that time. Nothing tied these computers together, especially computers of different types. But it was still a boom in a given workplace to be able to communicate electronically through the mini-computer. Now, I've included some hyperlinks in here to different articles that you might pursue if you're interested in looking at these things any further. So, time sharing, which was the phenomenon of putting multiple people onto the same mini-computer. There's an article here, and it's a rather short one, and it comes from Wikipedia, which for our purposes is credible. It is not academically credible. You couldn't cite this and have it be too credible in terms of a reference for an academic paper. But it actually is pretty good and descriptive, and I've checked out the articles that I'm putting hyperlinks in here too, so I would be comfortable in people reading this and taking some information from it and believing it. Anyway, time sharing, if you want to learn a little bit more about that, it's certainly possible to do. And here, if you wanted to see a little something about the early days of word processing, this article is already leaping ahead to word processing on microcomputers, but it's a good overall description of what's going on with word processors. And here in another place, it points to a program called Electric Pencil, which is one of the very first microcomputer word processors. So all these things, these office automation tools originate in the 1970s on mini-computers. But what comes along rather shortly thereafter is what I would characterize as the Wild West days of microcomputers, the period from around 1976 to around 83. Why those dates? Well, in 1976, the very first microcomputer was offered commercially, and it's this blue box that you see here on the right side of this little picture. Now, the left side is the Apple I computer, not the Apple II, but the Apple I. Both of these machines were sold as kits. This one came first. It was called the Altair 8800. And it was offered in the beginning of 1976 by a company whose name we probably, well, you wouldn't recognize at all, MITS. It's a microcomputer instrument technology, something or other S it stands for. In any case, MITS. Interesting story here was that the engineer in charge of this, Ed Roberts, and at one time some associates, manufactured scientific equipment and saw the potential for a small computer in the range of a few $100s for hobbyists, electronics hobbyists. And they offered this kit of parts and the cabinet all put together and the circuit boards all laid out, and you soldered the parts together, and if you did a good job and if you were accurate in how you programmed it with these switches at the front, you could actually run a program on this. Well, not very many people saw this as a very practical thing because you had to be a geek, basically, to do anything with this. And you assembled it yourself for a cost of maybe $500. And of course, back in 1976, $500 was probably like $1,500 or $2,000 as now. So you're talking about a fairly substantial investment here for something that really will simply light up red lights on the panel. Interestingly enough, here at DePaul acquired one of these. that generation. And the man who's now the provost of the university, Dr. Helmut Epp, was at the time in the math department, and we have a picture, a historical picture of him programming one of these things. It's hanging actually in the computer science office, and it's an interesting picture that I'd like to get a copy of and include in this workbook. I think I'll see if I can get permission to do that. In any case, this came along, and at the same time, in about the same period, two people, Steve Jobs and Steve Wozniak, in San Francisco, in the San Francisco area, also were doing the same thing. They cooked up a little circuit board for a group of hobbyists and hooked it up to a keyboard and came up with the Apple I computer kit. And they had no idea what the market would be for these things. They saw it just as a hobbyist tool also. It was a very interesting combination. Wozniak was apparently a very capable engineer, although he only got a degree after he became rich with Apple. But he could lay out circuit boards and economize on circuit components, and actually was the brains behind the electronic side of it. And Jobs was more the marketing, and it turns out the design kingpin in the firm. And you know what's happened since that time, Apple being a very major business with very fine products. Well, in any case, these folks at the time were also interested in the hardware. Another thing happened at about that very same time in the mind of a man named Bill Gates, who I think was perceptive in a way that perhaps the others at that point weren't. Apparently, Gates understood that software would drive this industry and not hardware. So when he saw an opportunity to build software initially for this MITS machine and later on for others, that's the origin of Microsoft actually creating a basic language compiler for one of these first computers. And then some very smart business deals after that. So that's 1976, this end of the range. Now, why 1983 as the end of this Wild West days of microcomputers? Well, in 1983 is when IBM unleashed its personal computer. Did I get that right? Was it 81 or 83? I looked that up. I lived through that, but it was a long time ago. So, early 80s, let's say. IBM finally legitimizes the microcomputer for the business workplace.
None of these actually had displays, right?
Well, these didn't have displays. They had to hook up to televisions or some type of other device like a teletype. And the input might be a paper tape reader, or it turns out eventually, cassette tapes with audio tones on them, the tones representing bits, just like a dial telephone, a touch-tone phone, except only two tones being used. So yeah, it was very crude. It was very crude. People who could see that these devices had some potential were rather visionary at the time. Well, their vision paid off in multiple ways and to the tune of big bucks. In any case, software is what ultimately would drive these things, and when IBM legitimized the idea that a small freestanding computer had a place in the workplace, at that time corporations began to take notice. This period from 76 to around 83, some people who actually bought some of the early machines tried to use them in businesses, and the management usually rejected the use of those machines because they felt that if the business came to depend on something like that, and the single person who built the application and ran it wasn't there any longer, then the business wouldn't know how to support this machine. And that's still the problem with software developed by end users with not very rigorous means and not much documentation. It is tough for the organization to become dependent on it because if the person isn't there, then they can't meet the need anymore. They may have forgotten other ways of satisfying that need. Well, in any case, the hardware was bubbling in this area. Lots of different manufacturers were putting out things. And the software started to standardize around a program called CPM, just a control program for microcomputers, which was, you might think of an early version of an operating system for computers. At least it was standardized enough that people who wrote programs could find a market with others who had one or another kind of computer that could accommodate the program because it was controlled by CPM. What happened in the early 80s, though, the very smart business deal that Bill Gates made, in cahoots with IBM, IBM was putting together their personal computer. And they looked around and thought it would be faster simply to buy the rights to an operating system that already existed. And here's where it really paid off to be the man in the middle. There was an organization in Seattle, I think it was Seattle Computer Works or someplace, that had developed an operating system to compete with CPM. And it worked on the type of architecture that IBM decided to use, the Intel line of chips. Well, Gates knew about this, and apparently IBM didn't. So when IBM went looking for an operating system, they went to Microsoft because it had already established a name for developing software for these small computers. And Gates didn't have an operating system, but he knew that Seattle Microcomputer did. So he offered Seattle Microcomputer $50,000 for the rights to what became the DOS operating system, PC DOS, for the IBM computer. And then he got, as the broker in between, had the software, the rights to it, turned around, licensed it to IBM, and became the kingpin of the operating system on IBM PCs. And as IBM PCs took off and sold, and eventually wiped out the small competition like these other machines that were kits or used various kinds of chips. There were a lot of them, and they fell by the wayside, just as when the automobile was developed. At first, there might have been 80 manufacturers, and that dwindled down to just a handful of manufacturers 20 years after the car was in production and people were buying them. So the same thing happened, and Gates rode that wave of popularity because his company controlled the software for the PCs. Well, the rest is kind of history because, of course, that business built into other businesses, and Microsoft is a very large corporation these days, still the kingpin of software in the small computer environment. Apple focused on hardware, and only in the last 20 years or so has been a major force, maybe perhaps even in the last 10 years, a major force building into a viable competitor to Microsoft, because it initially fragmented its hardware across a wide variety of different systems, and its initial success wasn't followed by success. And it was only when Jobs returned to that company in the early 2000s that they developed a focus and a standard for quality of their products and a style of product that really caught on. And they're riding that wave right now with the iPad and the iTouch 4th generation, and it looks like they'll continue to have a great deal of success in the future. So we have, essentially, looking here at these two machines, we have the precursor to the PC with Intel architecture here, and we have the precursor to the Apple line of computers here. Well, let's take a look at the software phenomenon that I mentioned was so important. In addition to Gates recognizing that software would drive this industry, not the hardware, another person came up with something that drove the Apple computer and sold tens of thousands of Apple machines. Dan Bricklin, very brilliant man, and a partner named Bob Frankston, a programmer, this partnership in business created the VisiCalc program, which stands for Visible Calculator. And this was in the late 1970s. To understand what this did, you have to understand that financial analysts and people who deal with the financial arrangements in corporations deal with grids of numbers, that is, rows and columns of numbers. The columns might represent time periods, like months, and the rows might represent various items of expenditure in a budget or various items of revenue. And the relationship between the columns is some type of formula. Perhaps a given row, the expenditure is constant throughout the year, so the 12 columns worth of the same number might appear. On the other hand, we might estimate some growth or some ups and downs in various columns, and formulas tie these columns together. But before anybody automated this process with a visible calculator, the process was manual. That is, you could put the numbers in the first column, apply the formulas yourself, and put the results in the second column. And you'd apply the same formulas to that column, and you'd put the results in the third column. And you might do that for 12 columns with an awful lot of calculation work going on. And then somebody would say, okay, wait a minute, let's do this. What if we assume that the growth rate in the third month is going to be greater because we're going to launch an advertising campaign? We want to put in the cost of the advertising campaign, but we're going to project a 3% higher growth rate in the sales of that product. So all of a sudden the third column starts changing, But because the 4th, 5th, 6th, 7th, all the way up to the 12th column depend on it, all those calculations have to be redone too. Because the point of this is to see what the bottom line will be at the end of the year. Well, that kind of calculation was the bane of financial analysts. Various people had attempted to automate that process. And in fact, I personally oversaw one of those efforts, a very crude effort written in PL1, not to be a general purpose tool, but simply to answer the needs of an analyst who wanted to have a 12-month spreadsheet. And a lot of programming was done, and she didn't get a chance to put the numbers in. It had to be somebody working with punch cards, putting the numbers in, and then running the program so that a printout would show what the result was. And others had done that in the 70s also. But what Bricklin did was to use a microcomputer to do that. He chose the Apple because the Apple was very, very affordable, and it was a very nice machine that was very simple. So he and Frankston wrote this visible calculator, and although it's crude by modern standards, it worked. It worked for the purpose very well. And all of a sudden, analysts could put the formulas into the cells where the numbers were intended to appear, and by putting numbers in the original cells, that is, the independent variables, and hitting the button, all of the columns would change automatically, because in sequence, from left to right, the columns would be recalculated. So by changing a number in the first column, you might affect every other cell within the spreadsheet almost instantaneously, at least very, very rapidly. Well, this was so popular, analysts just bought the machine to be able to run the program. And that proved the wisdom of the insight that the software would drive the industry, because the software is what delivers the functionality. So that's what started this explosion of Apple computer sales and actually set them on a path to be a competitor with Microsoft in a different kind of computer architecture. And from that, we have the two lines of computers that we find today. Microsoft, not manufacturing hardware, but manufacturing most of the software that runs on a wide variety of PCs manufactured by a lot of different people. Because essentially the Microsoft software doesn't care who makes the hardware. Apple, on the other hand, has maintained a monopoly on the hardware on which their software runs. And that's a stark difference between these two lines of small computers. With PCs, sometimes it's harder to set the software up because it has to anticipate all the wide variations in circuitry, the different kinds of processing boards for graphics and video and sound and a whole lot of other things. It used to be worse in the 90s. Now with machinery more powerful, operating systems more powerful, installing things on a PC isn't nearly as bad as it used to be. It doesn't require as much technical expertise. But Apple, on the other hand, because they control everything related to the product, the software and the machinery on which it runs, no one else manufactures Apple hardware.
Now you can run, like, hypothetically, if you wanted to run Apple's OS, you can run it on or install it on a thumb drive, slap it into a Windows computer. Originally, it would run Windows, but before you boot into Windows, you could boot from that flash disk and run Apple right off of there.
I'll bet you can't go into the Apple store and buy one of those.
Oh, definitely not.
Yeah, one student just mentioned that you could conceivably port Apple's operating system to a different machine, but it's nothing that Apple authorizes. And since they have a lot of lawyers, they would probably get on your case if you attempted to do that and sell that to other people.
I've never done that. I've seen it already.
Well, the intent, actually, the corporate philosophy of Apple is just to continue to maintain that monopoly. And that's one reason why Apple computers really are more expensive. They're very nicely designed. In fact, they're probably over-designed for the purpose, but you probably will spend 3 times as much on an Apple laptop as you would on a PC laptop. And they might be of comparable suitability for ordinary people. In fact, I just bought a laptop that cost me $469, and it
gets the job done the same.
Yeah, it gets the job done, everything that I have to do. So in any case, you paid your money and you take your choice. There are a lot of happy Apple users out there, and part of the reason is that it's a smooth process because no one has to integrate it on the user side. It's all the manufacturer that ties it together and guarantees that it's going to work. So That's just a little bit of the history here. I've included links to two movies here, two very interesting movies. There was a documentary made by PBS some years ago called The Triumph of the Nerds. And this is a very interesting movie, and there's a little clip here that you can see on YouTube. I'll just play just a little bit of it so you can see what it looks like.
The Apple II set a new standard for personal computers and showed there was some real money to be made. Rival companies popped up all over, but the market was still hobbyists. Guys with big beards who thought a good use for their computer was controlling a model train set.
So you can see what's going on with this movie. I thought it's kind of interesting. For 7 minutes, it will give you an insight into how the market looked at the time. Now, Bricklin is still around, although he kind of faded out when he sold the rights to VisiCalc to another company, and then I'm sure he's doing very well, but you don't hear his name all that much. However, he's still involved exercising his mental capacities in promoting Apple products, because here is an interview that you can see Dan Bricklin in 2010.
Today we're going to have information. We come to you from Boston, where I've bumped into Dan Bricklin, a famous character in the history of computing, the PC, and the internet, inventor of the spreadsheet, and a longtime friend. Glad to run into you here, Dan. And you've got a new piece of software out on the market. You just don't stop, do you? You just keep going. And so on this blank page, I can write something deep. And it shows up big here and small over there. Can you slide it over? Oh, no, I just broke the line. Because whatever you do, so I can undo. Okay? So I can use this button to move it over. Oh, I see. Okay. Or I can push the advance button, which automatically advances it past.
Actually, until I did the research on this particular page, I hadn't known about this product, but I thought it was very, very interesting. Once again, Apple has the hardware with certainly some vision about the software that can run on it, but creative people like this extend that. And in this case, it looks like Bricklin has come up with a very, very interesting and useful application for the iPad, turning it into a device that probably people expect that they could do things with it, to take notes in a very interesting way. So I have no idea if that product is offered, what it's called, but I suspect that it was available and perhaps at the application store that Apple runs. So in any case, that's what I'm going to tell you about the beginnings of the office automation, because actually what I plan to put into Unit 2, and I will finish up those pages today and get them out there so that all of these pages are in one bundle for you for Unit 2, probably about 20 or 30 pages worth of stuff in one PDF, page number 2. What I'm going to put in there is a little bit of information between what you've seen and what I'm going to talk about next that will deal with two aspects of word processing, spreadsheets, PowerPoint, that is presentation software, and databases. And the two aspects that I'm going to show you is to talk a little bit about where they came from, what they do, and of course the Microsoft Office product, but then also to give you some information about the Open Office suite of programs and some demonstrations of how they work, which are quite compatible with the Microsoft Office and are actually free, legally free, and of great interest to people who either don't have a lot of money or don't have a lot of infrastructure and resources for support, especially in third world countries where they could not afford to pay the kind of licensing prices that Microsoft charges. These other types of software are very interesting, the Open Office suite. The story behind that, Open Office was developed by the Sun Corporation, which manufactured computers and software in the Unix environment. They had
Java, right?
Yeah, they were the ones responsible for the development of the Java programming language. But the story I heard was that they had many, many thousands of employees, and they didn't want to pay the money to license Microsoft Office for that workforce. That workforce spread across different countries. So instead, they paid about $1 million and bought a German software company that had come up with a competitor to the Office suite. And then they just decided to make it available to everybody free. Well, I'm sure that doesn't please Microsoft, but in fact, it's perfectly legal to download Open Office, and which is something I just did yesterday, getting the latest version so that I could show you examples of it and demonstrations. And it's very, very nice. So that's the element that I'll include in the 4 pages that will be added into this about the 4 different office automation software products, personal productivity products, word processing, Excel, the spreadsheets, PowerPoint presentation, and a database software called Base in the open office environment.
What if they have to buy like the copyrights to Office though from Microsoft?
No.
Or I mean like the document itself, because then you can open Microsoft documents in their reader.
I don't know if they had to pay anything to Microsoft or not, if they just sort of analyzed the file and created different software to create the same format of file. I don't know if they really had to do anything, but there's actually no problem with it, because I'm sure Microsoft would have challenged it by this point if there had been. So I'll include that because it occurs to me that in terms of the life of a student and your own budget, you might find it more economical to use the open office software. It will produce files that are compatible with Microsoft Office. On the other hand, because this course is oriented to some extent to careers in the IT industry, then knowing about the open office alternative may be an advantage depending on the kind of organization that you seek employment with. So that's what I'm going to talk about in terms of the small computers. The next couple of pages, when they're available by tomorrow, will deal with the software products. But at this point, what I'm going to do is consider something that's at the tail end of this chapter, this Unit 2, which goes at the other extreme of, in a way, the other extreme of computing in general, commercial computing. So I'm going to tune into another page here, which you will get, but at the moment, may seem like it's so far disconnected from small computers that why am I saying it today? Well, I'm saying it today because it's the tail end of Unit 2, and this is the tail end of Unit 2. We're at the end of the 4th week, and this is the last lecture, lecture number 8, which wraps up Unit 2. Just in terms of progress, I'll have the exercise out there by tomorrow as well, and you'll have the remainder of the term to work on the exercise for Unit 2 as you do on all the other exercises. The projects for Unit 2, let's just say at least the deadline is a week from now, not this weekend, because you haven't had them from me until just recently. 4 of those projects are out there now, and you can take a look at them on the course website. The easiest way to reach that, of course, is www.c4e.us, and that's just an index page that lists several different sets of course materials. But to wrap up Unit 2, what I'm going to talk about is applications of supercomputing, and the page that you're looking at now, weather and nuclear modeling. Basically, this puts into writing some of the things I mentioned in the lecture the other day about the way weather analysis and weather prediction involves the use of very fast computers to do huge amounts of calculations that are necessary to implement mathematical formulas about the way the atmosphere interacts in cells that are of some considerable dimensions, how the gases work internally, and how they deal with one another over a distance. Those formulas could be implemented in computer form, and when you want to run that sort of a model mathematically, given the known conditions at the present time, you're trying to predict, okay, what will this look like, let's say 12 hours from now? The point I made the other day was that it doesn't make any sense to take so much computing time to do it that you don't have that prediction in advance. If it took you longer than 12 hours to make the prediction for the next 12 hours, then it's irrelevant. So an awful lot of computing horsepower has to be applied to this. And once again, since we're looking at careers, here's a link to a place that will give you information about this field of meteorology. I'm not trying to scare you with all those formulas. What I wanted to point out down here was just some definitions and some ideas about that career field, what it takes to get into that field if you happen to be interested in that. And then there are some links in here which you can follow as well. It involves a lot of math if you were involved in those models themselves. Now, the TV weatherman doesn't know that. The TV weatherman probably went to the journalism school and learned how to speak in front of a camera and to read things from a teleprompter, and may not have a great deal of knowledge any more than you or I might have about whether it's raining outside unless he looked out the window. But he has access to information produced by meteorologists who then make these predictions based on the kinds of powers of these computers that we've been talking about. Now, another type of scientific application of supercomputers is modeling things like this rather ominous mushroom cloud here, nuclear reactions and explosions. The same kinds of models the same type of thing that can be done here with mathematics to model the way the atmosphere works have actually been written to model the way that atomic particles interact with one another when they're jammed together with such intense pressure and heat that they either fuse into other materials, a fusion bomb, or they split atoms apart in fission bombs. Well, it used to be that in manufacturing these weapons and testing them and developing ever more powerful ones, the weapons would actually be constructed and then blown up. That's kind of nasty to do. It's nasty to the Earth, and it puts a lot of nasty things in the atmosphere. For a time, the bombs were tested underground. There are some problems with that as well. It's much cleaner if nuclear reactions are studied mathematically, but the number of calculations involved in doing that is astronomical, because we're talking here about trillions and trillions of particles interacting with one another. And although mathematical formulas can be written to predict how those interactions will occur, running the numbers on that is even much more time intensive and computer power intensive than it is for weather prediction. Related to that is Earth movement studies, and the reason this little map is in here and the little red dots on it are actually locations of earthquakes. These same types of programs can be written to analyze the sensings of movements in the Earth to detect earthquakes or to detect nuclear explosions occurring underground elsewhere. This type of thing is also highly mathematical. There's a paper here that I found kind of interesting that you might find interesting if you have some interest in that area. And here it's modeling for nuclear explosion monitoring. It's a very technical paper. I'll just go into it a little bit. And if you read through this abstract and it makes you have a warm and fuzzy feeling, you might be interested in pursuing additional knowledge in this area. Once again, very mathematically inclined and interesting to people who might want to pursue that type of career. So in any case, that's just another resource that you might explore. Found that rather handy. Now that's as much as I'll tell you about that type of computer, a large supercomputer. What I'd like to consider right now is a third type of computer that you probably have not even thought about very much, because these computers tend to be small, perhaps even smaller than personal computers, and they're hidden.
ECUs.
What's the ECU?
They have them in cars. I think it's electronic computer or something.
Oh, sure. Yeah, that's just one application of this sort of thing. In fact, these little hidden computers, called embedded computers, they may use chips that are not very familiar to us, that are manufactured for very special purposes. They may have less computing power than even a PC, because they don't necessarily need a great deal of computing power. What they do need is to be made rugged, because they're many times put into environments where the temperature or the pressure or the mechanical shock is very great, for example, in an airplane. An airplane might have many, many of these small computers in there doing various things in the navigation system or in controlling the surfaces of the aircraft that make it go one way or the other.
I was mistaken. It's an electronic control unit. According to Wikipedia, a generic term for any embedded system that controls one or more of the electrical systems or subsystems in a motor vehicle, or I guess airplane as well.
Yeah, an ECU. And another term, another acronym is PLC, for Programmable Logic Circuit, that may be a small chip on there that actually might be set to have memory embedded, an electrically reprogrammable read-only memory. Well, in any case, here's one of the more interesting ways that these embedded computers are used. You might have heard the term fly-by-wire used in connection with newer aircraft. What happens in the fly-by-wire environment is that, think about an aircraft that is it's called hypercritical. It's designed to be very high performance, like a fighter jet. It's going to be going very fast. It's going to have wing surfaces that are very critical in terms of their adjustment, and a pilot may not even be able to control it adequately because the human reaction time is too slow to control this. The stealth fighter is like this. It's not really very stable. It has to be controlled by a computer that senses things and controls those surfaces very fast, almost like an automatic pilot, except it's controlling the stability of the airplane. Anyway, fly-by-wire means that the pilot is one input to a computer, and the computer's output is the thing that determines how things are set and make the airplane fly. I'll give you an example of this. A crash that occurred in 1989 occurred in Iowa, where on a 3-engine jet, the engine in the center on the tail, the rotor in it blew up, and it tore out the hydraulic lines to all of the wing surfaces, the flaps and everything else, and the rudder. And there were several hundred people on this aircraft. The pilot, very quickly, a number of people in the cockpit and a pilot who was traveling, and wasn't flying the plane at the time, joined the effort, and then air traffic controllers on the ground. They managed to control the aircraft enough by varying the speed of the left engine and the right engine that they could make wide sweeping turns with it. And by varying the amount of thrust, they were able to make the airplane descend. Instead of crashing, they were able to sort of bring it in. And they were able to land. It was a horrible crash landing in Iowa. And a number of people did get killed, but about 200 people of the 300 on board survived, which was miraculous because all of them were headed for doom. With that kind of damage to the aircraft, if the pilot and the rest of the people working on that situation, they were very lucky that the airplane, by way of their cruise controls, could sort of line up to a runway. And they were very lucky that the plane held stable as long as it did. Otherwise, it was pretty certain that certain death for all of them. But if you think about that, here's an aircraft that is very difficult to control because it has lost most of the control features. The only thing that could control it was varying the speed on these two engines. Well, with a fly-by-wire system, which has now been installed on aircraft like that, the pilot is one input to the computer. The computer is reading inputs from all sorts of speed sensors and attitude sensors and all sorts of other gizmos that it's becoming informed about the performance of the plane. So in a situation like that, because that computer is controlling everything to simulate normal operation of the aircraft, landing that aircraft, even as damaged as that, would be a fairly normal experience to the pilot. Because the computer has been programmed to take into account every little variation that might be possible in the engine speed and the rate at which it's changing and the proportion of thrust out of each engine to try and control the plane as normally as possible. Now, in ordinary operation, what fly-by-wire does is the pilot may give the main input to the computer, which is the direction the airplane is going to fly, and the computer, by way of reading the sensors indicating variations in air pressure and the way that the airplane is moving, may smooth out the whole turn, may smooth out the ride of the aircraft, so that it's assisting in the control of the surfaces of the aircraft, making for a better trip in the airplane, basically, and more control over the aircraft. Well, that kind of computer is an embedded computer. In fact, I'll give you a little other information about fly-by-wire. Because it's so critical that the computers operate properly, the real requirement that's imposed is that 3 computers are used. And the computers have to be programmed in different languages and manufactured by different vendors. And the 3 computers then are all processing the same information, and another computer takes a look and compares what they're saying. And if there's differences, it takes the 2 that are closest together and relies on them. It's just like in the days of sailing ships, where a clock was very important for navigation purposes. The rule of thumb was the captain of the ship either took 1 clock or he took 3 clocks. If you took 2, you wouldn't know which one to believe. So if you're going to have multiple clocks, you take at least 3. and then you sort of poll them, and the two that are closest together are the ones you believe. And the same thing is done with fly-by-wire systems with these kinds of embedded computers. Now, a much simpler mechanism exists in a car with a cruise control. This is an embedded computer, and I've introduced the term here, servo mechanism. The servo mechanism maintains an equilibrium between things. So what's happening is the driver sets a signal here that basically says how fast the car is supposed to go. The computer, the little embedded computer, reads that and is also reading the speed of the car. And it compares these two values, which have been digitized so that it can do this with a little digital program. And if the car is moving slower than the signal, that is, the speed indication is lower than the setting that's desired, the computer gives the engine the signal to speed up. And it keeps measuring things, and finally the engine speeds up enough that it might even be pushing the car faster than the setting, and so then it cuts back and it tells the engine to go a little bit slower. So this thing, one machine, namely the computer, is controlling another machine based on sensing what's happening with that machine. In the old days, let's say with a steam engine, this was done mechanically with what was called a governor. So you could set the governor so that the engine would go a certain speed, and mechanically it would cut back on various things if the engine overspeeded. But now this is done electronically, and it's done more reliably this way because the sensing devices can be more precise, and the computer program can be set in such a way, or perhaps varied, because the control here is actually varying one of the inputs, so you can vary where you want the setting to be, and the equilibrium maintained by the embedded computer program, the embedded computer acting like a servo mechanism, will control this. So here's two links that you might find interesting. One is just about servo mechanisms, a description of a servo mechanism and a little illustration here of an actual piece of equipment, some discussion of the history behind them. And here, I thought you might find this article interesting because this gets into a type of application called process control. And I'll give you another example of it as we wrap up our discussion today. But process control is actually what's happening here. Here's a mention of programmable logic controller, which is a component of that. Basically, we have here an independent variable. In the case of the speed control, it would be the setting. And then we have the dependent variable, which is the actual result, the machine being controlled at that speed. So you might read this if you're interested in this type of mechanical and engineering orientation. These kinds of computers are not what you would consider general purpose computers. They may be programmed in languages unfamiliar to people who program in more business-oriented ways, and they're hidden, so that these would be jobs that would exist with manufacturing companies, not well publicized perhaps, because in some ways they even come up to be competitive advantage. Let's take a look at an application, though, that I think you'll find rather interesting in the area of process control. And this is an example from a course that I used to teach here at DePaul that used actually a simulator of one of these very small process control chips to have you write programs that would do things like the problem that I'm describing here. So here's an example of a process control application, kind of a modern one. Here we have a satellite that's been made to orbit the Earth, and perhaps it's relaying radio or television signals, or it's a GPS satellite. It's going to be up there for a while, and it's going to generate power with solar cells. In order for the cells to generate maximum power, they have to be flat to the sun. That is, as this thing moves, the position of the satellite has to change because it wants to maintain the solar cells flat to the sun so that they receive as much light as possible. And here you see two different orientations of this, with the sun being here. In both of these situations, with the panels not head on to the sun, they're going to receive less intensity of light and they'll generate less electricity. So two problems exist here. First of all, how do you detect the position of the satellite and the solar panels in relationship to the sun? And another one that's a little more subtle. How are you going to move the position of the satellite with respect to the sun? That second problem, let's talk about first. It's an interesting problem. It doesn't have anything to do with computers, but when I thought about this, I sort of puzzled it out. I was stuck on a bus between Minneapolis and Chicago, and I didn't have any access to the internet to look things up. So I was sort of thinking about this, and it was an interesting way to spend 12 hours on a very slow bus ride. I was glad I had the problem to think about. How are you going to do this? The thing most people suggest is that, well, we're going to have a little jet out there, and we're going to have some compressed gas, and when we determine we're going to have to move this, we're going to squirt out a little puff of gas so that the reaction to that will be to move the satellite in a different direction. Yes, that would definitely work. But the problem is the satellite's going to be there for a long time, and you're not going to have an unlimited supply of gas, and you're not going to be able to manufacture more of it. The only thing you can manufacture in terms of energy is electrical energy. So with that renewable resource, how are you going to position the satellite so that you don't have something like the gas that runs out and then you can't do it anymore, you can't control it? Well, it turns out what actually is used in the industry in doing this is called a momentum wheel or a reaction wheel. And there are usually 3, maybe 4 of them in the satellite. Think about it this way. You have 3 different directions, right? Up and sideways and forward. So 3 axis of rotation hanging there in space. Now, if you've ever used an electric drill and you turn it on and go fast, it kicks back on you because the rotor, you're attempting to speed it up and it's going to kick back. It has inertia. It doesn't want to get started up. It resists that change in its rotational speed. And in fact, it's a general thing. Even if it's rotating and you attempt to speed it up, it's going to kick back. Or if you attempt to slow it down, it's going to kick in the other direction. This is what's used to position the satellite. And the reason for at least the 3 of these momentum wheels is that you need them to be able to control the attitude of the position of the satellite in any of these 3 planes. Actually, a little bit of an aside that isn't mentioned there, they do have a 4th one that comes out at an oblique angle, and that's a backup on all the others. You wouldn't want to have 6 of these out there because weight in a spacecraft is a big consideration and power as well. But by having one come out at an oblique angle and doing some pretty complex programming, you can have it take over for any one of the others failing, and perhaps even 2 of the others failing. You could achieve some element of control with more complex programming. Well, the programming is fine because that's just little bits being stored someplace. Even though it's complex, it's possible to do it. And the extra one may be used to store energy. That is, it's a form of battery. The cells are generating electricity here and now. If you don't have to consume the electricity now, you want to save it. Well, how do you save energy? In a battery, batteries are kind of heavy. If you have this 4th momentum wheel, you can store energy by speeding it up. And then you can recapture the energy by having it drive some generator to get it back, maybe when the satellite's rotated around the other end of the Earth and the sun isn't around and it can't generate electricity for itself. So pretty clever engineering in satellites. But basically what happens here is this. Let's get back to talking about an embedded computer system. Here's the situation. A sensor might be as simple as this. Just a little pyramid-shaped thing that has on each of the 4 faces a little solar cell. And what will happen is these cells will generate the same amount of electricity when this is pointed flat at the sun because both the sensors have the same angle that they're receiving energy. But when it's out of position, one's going to generate more electricity, more signal than the other one. This will be almost in shade, and this is almost face on, so it's going to generate a lot. And that's the difference. The difference here is what the Servo Mechanism of an embedded computer program will attempt to do. It will say, okay, there's a difference in response to this one being bigger than this one. Let's send a signal that affects these momentum wheels in such a way that this thing is turned in this direction. And once it goes in that direction slowly and it starts getting past the point, then this one starts generating more electricity than this one, and so it gives signals to counter that, and eventually it just settles down to be pointing straight at the sun, which is what you wanted. So this is very interesting. This gets more into engineering, but it's an interesting application of an embedded, that is a process control system that I think you could readily understand the need for it and how it's doing this. If you're interested in this particular career field. Here's a resource for you. This gets into aerospace engineering, and here is some prediction of what the opportunities in that field might be, and some indication of what it pays in terms of salaries at the present time. But I just thought I'd give you this link so that you could pursue that if you were interested in this aspect of it. This is taxes your abilities in terms of solving puzzles, also is mathematically oriented, gets into engineering, and various liberal arts fields are a good precursor to that. So that is what I wanted to cover in terms of embedded computer systems, to give you an idea of that. Now, these pages, as I mentioned, will be out there, and all of Unit 2's pages will be packaged up for you, including all 5 of the projects that are potential projects for you. And I can finally get the exercise out there because I need to base them on the writings and what you view here, and until they're made known to you, then the exercise wouldn't make any sense. So that's as much as I'm going to say today, and we have here at 10:45, we've concluded the lecture, and I'll put up the slide that indicates that for the people who are tuning in online. Do take a look at the course website between now and, let's say, the end of the weekend, because you'll see many more things there. This is the 4th week of the course wrapping up. We have 3 more units after this, and I'll start putting the material for next unit out there. All the material is available for you online, which I think has some impact on the amount of attendance I'm getting right now. I do suspect at some point the room will be empty, and I will be making this lecture, and that's fine. Except in the future, I'll record these lectures in front of a camera, and I won't have to come to an empty classroom to do it. And perhaps I'll make the illustrations and the slides even bigger. Anyway, if you have any questions, do email me at csc200winter@gmail.com. I am completely caught up as of last night with the grading on everything that's been turned in. So I'm just waiting for more things to come in, and if you have any questions that are, problems that are preventing you from doing the exercises or doing the projects, please let me know. We're going to get into, in the next unit, some very interesting, more contemporary uses of computing, including picture editing, sound recording, sound editing, video recording, and video editing. I think that's going to be kind of a fun unit, and you can participate in a number of ways with whatever type of equipment you have, because the sound editing software is free. It's called Audacity. You can download it for a PC. You can download it for a Mac. So some of the projects will deal with that. The digital pictures, it's possible to do things with pictures that you take or images that you find on the web on Google. So, and the software for doing work with that is already on the web. So everybody will be able to participate there. And the video editing, it will be different between the PC and the Mac environment, so I'll be giving you some material on both of those and some links to videos that will help you complete those assignments if you choose to do those projects. So I think you're going to enjoy the next unit. Let me know if you have any problems, and if not, here it is Thursday morning. I hope you have a nice weekend. Bye-bye.